Earth's ice plays a really incredibly important role in the climate system. It affects many different parts of how the planet's atmospheres and oceans behave. The ice that's lost from Antarctica and Greenland causes the water to be fresher and cooler than it otherwise would be. That's really important for driving thermohaline circulation, which delivers heat to parts of the planet where we like to have it. But also the ice that's lost from the ice sheets causes sea levels to rise as well, and so there are many different reasons to study the polar regions. And of course the best way to do that is with satellites. This is a beautiful picture of the Greenland ice sheet taken by the Space Shuttle about 10 years ago when it was flying at about 200 kilometres altitude, and it gives us a view of the ice sheet that we really hadn't had before at all. And we can see how the ice rests as a lump in the middle of the island of Greenland, but is drained through these very narrow fjords where icebergs carve off and they drift into the oceans and cause things to happen, things that if you're a shipper we wouldn't want to happen. So you want to be able to track those icebergs, and we can do that from space. The hydrological cycle is really quite simple. Most people understand that water evaporates from the oceans and drifts around the planet and falls as rain in some parts of the planet, but as snow in the polar regions. And it's that snow and the accumulation over tens of thousands of years that forms an ice sheet, a solid lump of ice in Antarctica and in Greenland. The ice then starts to compact and move through its own weight and drain out into the oceans. Sometimes it drains just onto land and it melts, and that water runs off and pours back into the oceans to complete the hydrological cycle there. But in other places the ice flows out into the sea and either carves off as tabular icebergs and they melt somewhere else, or we get very rigorous melting beneath the floating sections of the ice shelves. This is really, it turns out, a really important part of the planet, and a little understood part of the planet, at least before we had satellite measurements which told people how important it was. The amount of ice that's lost from Antarctica, in fact, is huge in comparison to what we used to think it was beneath these floating ice shelves. And that's really important. It turns out that this junction here, where the ice sheet starts to lift off from the ground and starts to float, is a really key part of the ice sheet region, and we can monitor that from space. So if we look at the rate of sea level rise as it's happening right now, we were able to measure the change in global sea level with satellite altimeters. And it's rising by about 2 or 3 millimetres per year, and has been doing over the past 20 years or so. Half of that is due to expansion of the oceans, because they're getting warmer and the oceans expand a little bit. So there's no change in mass, but they do occupy a larger volume. And that's a pretty easy part of the sea level budget to measure. You just measure the ocean temperature, and to predict into the future, because it behaves quite well. Changes in the planet's temperature over time will correspondingly increase the rate of thermal expansion. We have a contribution from glaciers and ice caps. They're the small bits of ice that are not in Greenland or Antarctica, often up mountains. We like to ski in those places. And actually it turns out that about 0.5 millimetre per year is occurring because of loss of ice from those parts of the planet. And the large ice sheets in Greenland and Antarctica, which contain 99% of the fresh water that's stored above sea level, are actually causing just a small contribution to global sea level rise right now, maybe 10% over the past 20 years or so on average. Why should we be interested in Antarctica and Greenland? Well, we're interested because of the potential contribution that they could make. There's enough ice in Antarctica and Greenland to cause sea levels to rise by about 60 metres or so. This is a curve, it's a familiar curve from the IPCC assessment report, the last one, showing what people think will happen to sea level over the next century. And there are contributions from lots of different terms. There's thermal expansion, as we just discussed, glaciers, Greenland ice sheet, Antarctica, land water storage, and there's an additional term here which I'll come back to, rapid dynamics of the ice sheets. And overall, the IPCC has suggested that sea levels will rise by about 70 centimetres over the next century. And that's important. Even that rate of sea level rise will be an important number for people to take into account. But as a glaciologist, we know that there are things missing from this assessment, and so do the IPCC. And those things that are missing are how the ice sheet could behave if things didn't behave as the models that we use to predict future changes expect them to. So this contribution here, Greenland ice sheet rapid dynamics, is almost insignificant. You can hardly see it at all in the sea level budget, but we know actually that things are changing quite rapidly on the planet. In different parts of the cryosphere, we see changes that are just not reproduced in these models which are used to predict sea level rise. And these processes can cause the ice sheets to flow more quickly and discharge more ice into the oceans than any of these models predict. And what's important is the potential contribution that the ice sheets can make. So if we look at Greenland and Antarctica, clearly they're very large continents. We need to use satellites to be able to survey them. We couldn't possibly hope to look at the ice that's stored in Antarctica and Greenland on foot. And there's enough ice in these ice sheets to cause sea levels to rise by, in the case of Greenland, more than 5 metres. In the case of Antarctica, more than 50 metres or so. Now, no one expects that to happen anytime soon, but it's important for us to be able to understand what the potential contribution might be and what the risks are of that happening. With enough ice to raise global sea levels by almost 60 metres, the polar ice sheets do pose a considerable threat to many parts of the planet. This is a map of the UK, how it looks like today, and this is how the UK would look like if we had no polar ice sheets at all in Greenland or Antarctica. That's clearly an extreme scenario, very unlikely to happen in any short time scale. If you look at the geological record, it has not happened in anything like a rapid time scale. But we can get large fluctuations in sea level rise. And we see from the satellite records many different examples of the changing climate system. This is a photograph taken in 1993 of Mount Kilimanjaro in Africa. And it shows a large area covered by some white stuff, which could be ice, could be snow. This is a photograph taken 7 years later. And of course, there's a big difference. But this is not, in fact, a signal of climate change. This is just weather. This is on one year we had a large covering of snow, and another year we don't. And that happens a lot in different parts of the planet. But there are very good examples of rapid climate change on the planet, and the Arctic sea ice retreat is a classic that most people are aware of. The extent of Arctic sea ice in the Northern Hemisphere has retreated by about 30% in summer over the past 30 years or so. That's a huge reduction, and it has an important impact on the climate system. The albedo of the planet changes, and the heat storage then changes as a result of that. The problem that we have is that the models that we use to predict how the planet will change over the next century don't even reproduce the observations that we have today. So this is a curve that shows the area of sea ice and how it will develop over the next 20 or 30 years. The brown shaded region is the average of the model simulations, and you can see in the blue curve, the actual observations, the models don't even overlap with the observations today. So we can't have a great deal of confidence in how those future predictions will pan out. Without accurate models of, in this case, the Arctic sea ice system, we have to rely on satellite observations to tell us what's in fact changing. There's another very, very good example of rapid climate change, and that's at the Larsen ice shelf in Antarctica. This part of the planet down here. I'll just zoom in, and we can see in this Google Earth image of Antarctica, the Larsen ice shelf, how it stands today. So this is a part of the ice sheet that is in fact floating on the ocean surface. And we can see that, it's really, really flat over here. You can see that in this image here, but you can also see it in this image here. These are the mountains which supply the ice shelf with ice. The glaciers flow down into the oceans, and they fill this protected embayment with ice, and it rests on the ocean surface. It's very, very different to the sea ice in the Northern Hemisphere. It's about 500 metres thick, so it's a substantial block of ice, and it's been there for some time. In this image, you can see here that parts of the Larsen ice shelf are no longer present. The northern tip of the ice shelf has now disappeared, and I'll explain to you how that's happened and why that's happened next. So if we zoom into this part of the animation, we can see a sequence of satellite images that have been collected over the Larsen ice shelf over the past 20 or 30 years. And successively, we see parts of the ice shelf disintegrating, collapsing, drifting off into the ocean. So this is 1986 here, when the ice shelf was intact. But progressively over time, and I'll stick a ship here just to remind you that this part of the image is open ocean, and the ship can sail around here, but the ship can't sail where the ice shelf barrier is because it's 500 metres thick. And so if we march through time, in 1992, some of the ice shelf had disintegrated. And as we progressively move towards closer to the present date, you can see that a very, very large chunk of ice disappeared from Antarctica and is now part of the global oceans. And that part of the ice shelf is considerably large. It's about the size of Greater London, for example, for context. And the question is whether it's an important signal of climate change. And we can look at what's happening in that part of the planet at a later date, and this has happened now. People have sailed into the embayment and collected measurements to see if we can understand something about the history of this part of the planet. And we can do lots of nice things from ships. We can collect measurements from the sea floor of different samples from the mud and the rocks and the shells that are present on the sea floor and analyse them to try and reconstruct the past environment in this region. That's what was done, and a piston core was collected, and this is an image of the piston core here. This is one section of the core, about 50 centimetres, and people analyse what's in that part of the core and try and date it and try and understand the past environment. And there are some really clever things that you can do with marine organisms. This is a marine organism. It's called a foraminifera. It's a little shell, tiny shell, about a micrometer in size. And this shell likes to live in light environments. And there are other shells that like to live in dark environments. And if you track the abundance of these shells in the sediment core, you can start to reconstruct the environment that was present at different times in the past. And what we can tell from this is that for the past 5 to 10,000 years, this part of the sea floor has been dark. That means that there's been an ice shelf resting on top of that part of the planet for about 5 or 10,000 years. So the events that we've seen today, the collapse of the past 20 or 30 years of the Larsen ice shelf, are unprecedented in the last few millennia. And that tells us it's an abrupt climate change, and we ought to pay attention to that. And it's even more important than just the loss of the floating ice itself, because the glaciers, this is now some more sophisticated data collected from satellites measuring the speed of the ice, are now flowing a lot more quickly into the ocean. So this is Drygalski Glacier at the Larsen ice shelf, formerly draining into the Larsen A ice shelf, but now flowing straight into the open ocean. And this Drygalski Glacier is now flowing 8 to 10 times as fast as it was before. That's really important because it's putting more water into the oceans, which means it's causing sea level rise. So this part of the planet, the Antarctic Peninsula in general, here, it's only about 4% of Antarctica in total area, but it's delivering a quarter of the ice losses from the continent. And that's because it's situated in a very, very northerly part of the ice sheet. It's the most northern tip of Antarctica, and so it's the warmest part of the ice sheet. So why is this important? It's important because these rapid and abrupt changes in the climate system are not incorporated into the models that we rely on to predict future sea level rise. This was known, and is still known, at the time of the last IPCC report in 2007, the fourth assessment report. The models used to calculate sea level rise do not incorporate the full effects of changes in the ice sheets that we know of today. And it's still known about today. There are significant challenges that remain in the projections of the ice sheet losses because of the uncertainties associated with the processes of rapid ice dynamical imbalance that we can see from the satellite measurements. And so it's really important to continue to collect satellite measurements in the absence of accurate models, not just to inform people of how the cryosphere and therefore the oceans and sea levels are changing, but also to help us to build better models in the future to predict sea level rise more accurately.